Inheritance in UML typically referred to as generalization. So it sort of implies that we can have a pretty generic concept that is sort of much more abstract than other parts of the system, and related classes could then be more concrete, and so be less generalized and more concrete, less abstract and more concrete. So UML likes to name these relationships generalization relationships. However, programmers often use inheritance relationships. The core concept of this relationship is that dog is a mammal. All right, so it's an is-a type of relationship. And together, these relationships and classes involved in this relationship typically form a hierarchy of classes. So the benefit of having a base class, the class that has common parts, that we don't have to repeat any of this in subclasses, in these derived classes from the base, which means that both dog and cat will have definitely an iColor attribute, and they will be able to use this operation get iColor, right? And so methods specific to these type of mammals right here, dog and cat, will have their own specific attributes, but this is the part which is common to both of them. By the way, commonalities should be sought very, very actively. They are extremely beneficial because they just benefit the structure, they benefit the correctness of our class design. So search for generalization and classification of concepts are high-level activities that yield lasting results. So this is probably one of the most important activities during the use case analysis. So in Java, in inheritance, we typically refer to classes at the top of the hierarchy, the most generic classes, as superclasses, but other terms are used for defining base classes, also known as parent classes, and also known as base classes. So C++ traditionally uses terminology base class for the classes on top of hierarchy. Java traditionally uses the term superclass. And a lot of times you can refer to parent-child relationship between these two, but I think the terminology in technical terms, parent-child, is more successful in describing a network of nodes of a data structure, such that you can have a tree with a root or parent object, and it can have its branches identified by children and siblings and all that type of relationship. So it's more of a connect specific or in context of some sort of connections between the objects. Parent and child is more successful terminology. In Java, it's very typical to call superclasses and subclasses at the bottom of the hierarchy. So the hierarchy is not limited to only one level of relationship. You can easily derive other, even more specific concepts from each class which is already defined in the system. A typical approach in class hierarchy design is that the base classes have no knowledge about the classes that derive from them. Right, so superclass is pretty independent and it has its own life cycle, and the derived classes have to basically deal with what they inherit from the base classes. So superclass, subclass, base class, derived class, that's the terminology here. Okay. As I already mentioned, a generalization relationship typically is understood as is a relationship. Okay, so for instance, if we have a shape, shape is abstract concept. It does not specify if anything specific. For instance, if I am asking you to draw a shape, your question will be, what kind of shape should I draw? Right? So this is just impossible to just jump to the board and start drawing a shape, okay? Unless you want to draw a random shape, which is basically outside of the scope of the idea of is a relationship. But basically, when we want to draw a circle, we need to have a circle definition, or a star definition, or a square definition. And then in this kind of relationship, we can say that circle is a shape, star is a shape, or a square is a shape. So is a relationship suggests that both circle and square are shapes, and note that these things can independently draw themselves, right? So they define the draw operation all over there, but shape can basically used to shape interface perhaps should be used to access the functionality of each single one of them. So this would be the common parts of each shape, like location of the center of each shape, for example, can be saved in base class name shape. So this architecture supports polymorphism or polymorphic behavior of, in our case, an example of a shape. And so polymorphism stands for uniform interface, and each derived class inherits the base interface. All right, so what happens here, and I think we discussed this in one of our previous videos, is that operation can be declared at the base hierarchy level, and then it can be implemented in derived classes. And if then we have a system that, for instance, keeps track of shapes in a container, so we have a container that stores references to shapes. Okay, so we can define a class container of drawings and have a collection, like an array of objects in this class, and each element of this array is a reference to a shape. By using this reference and making calls specifically into getArea, the shape at runtime will dispatch this call to the corresponding actual underlying object and will be able to invoke the getArea specific to a rectangle or a circle, depending what real shape this is. So this is an idea of polymorphic behavior, and so each derived class provides its own implementation, and for each of the abstract methods declared at the shape level. And when a message such as draw or method call such as draw is sent to an object of type shape, it is dispatched to the distinct method of the actual object which is implementing this specific shape. So here we have an example of the code where we have getArea as we try to use in this example right here in UML, but this is an example where we say getArea, and notice that we provide semicolon, which is not providing an actual implementation, and in Java we use abstract keyword. In C++ we would be using virtual keyword. And we declare this method to be a public abstract method, and this suggests that using the shape class as a reference to an object such as rectangle or a circle will permit to make a call into the actual implementations. So for instance, rectangle, which is extending the shape, and circle, which is also extending the shape, we provide getArea, and of course for the rectangle we multiply it by the length and width, and the area of circle of course is defined as pi multiplied by radius square, or in this case we just say 3.14 times radius. Okay, so this is an idea of using inheritance as a foundation, the structure which permits this polymorphic behavior, that typically step number 1 in defining the structure to utilize this polymorphic behavior is that what we do, that we create an array, and the type of elements stored in this array are references to shape. Okay, so this is an array of each element here is a reference to a shape. However, when we create actual shapes, so this is an array object right here, right? So this is some sort of object in memory. And when we define actual shapes, we don't create shapes, we create rectangles that look like objects in memory, and we create circles that also look like objects in memory. And each single one of them has its set of attributes, like length and width of the rectangle and radius of a circle, so their internal structure is different. However, we use uniform container which is pointing to each of these objects, and so this is a reference to a rectangle, and this is reference to a circle. And when in runtime we call getArea for any of these elements of this array, what is going to be happening, that if it happens to be the rectangle underlying object that was put into this container of shapes, then if we make a call into getArea, the call will be dispatched into the implementation of getArea of a rectangle. But if we at the same time make a call and it happens to be that this object is a circle, the call will be dispatched to the implementation of getArea for the circle, which is exactly what we're trying to describe here, which is the polymorphic behavior. So this is the demonstration of this idea, is that we create a circle and we create a rectangle. And when we create a circle, we specify what is the radius. And when we create a rectangle, we specify the height and width parameters. And then we try to print getArea for circle and getArea for the rectangle. And we pass it to the method named getArea. And this is our static method because it's been called from the static main method. But what we return here is an actual shape, right, which returns getArea. So therefore, this print statement will be able to compute the sum of both circle and rectangle areas quite successfully. This will be, at this stage right here, this will be the polymorphic call, because it will be specific to the either getArea of the rectangle or getArea of the circle. But you can see that this same line physically calls two different methods. So this is an example of this uniform approach, that the same line can dispatch, can direct the call to the specific implementation depending on what kind of shape this is.